is the separator. The discuss the effective landing on soft snow is the second part. So I might do the soft snow part first because that's a little bit easier. And it's kind of not related. There's a trick in this. This equation we're trying to derive is not related to the second part. You could do it that way. You could use forces. The reaction forces change momentum over the change in time, and in this case, if B is going to increase, so B is going to increase because you've got the compression of the snow. Okay, so the snow compresses, and that adds an extra little bit of distance to B in this model. That's going to increase the time. So if you increase the time, you're going to decrease the force. Okay, according to that impulse model. So that's kind of an explanation of what's going on. But if we go back to our original formula, Fr equals mg again, and then we've got h over b, so 3 meters, 3.0, sorry, I should have done that in the first place. 3 meters, which is 3, and this time we've increased b, say 10 or 20 centimeters. The answer gives 10, assumes about 10 centimeter compression of snow. It really depends on how deep the snow is, doesn't it? But that would mean this is 0.6 plus 1. 3 over 0.6 is now 5. So 5 plus 1 is 6. That means you've got 6 mg. That means you've decreased the force by a significant amount, 1/7 of the force. And you imagine the more you increase the compression of the snow, the lower that force is going to get. Okay, so now we need to derive T equals B square root 2 over GH. And there's a couple of approaches to this, but we're just going to stick with keeping it simple. Keep it simple, stupid. Whenever you're looking with time, the time to come to a stop, you've got your velocity is distance over time equation. Remember, V is going to be your average velocity. It's not going to be instantaneous because you've got that acceleration. There's the bottom of that unusual graph which shows that your acceleration, if your acceleration is proportional to the force, the acceleration is going to peak halfway through, which means your velocity is not constant. But for the sake of this, velocity is constant. D in this case is B, and the time is the time which we've got above there. So now all we need to do is find this average velocity, and the square root and the GH and give me a bit of a clue that we're going to have to equate the gravitational potential energy with the kinetic energy. So at the start of the B compression, okay, so the point where it just touches the snow but before the knees have started bending, all of that mgh is going to be equal to that half mv squared. Okay, so your kinetic energy has your gravitational potential energy is converted to kinetic energy. So we can cancel out the m's, and then we've got, remember, this is going to be our average velocity, VAV, okay, because it's constant throughout the whole deceleration process. Remember, if that force is constant, the hang on, no, that doesn't work because constant force still means there's acceleration, but we're dealing with this. Oh, hang on, no, I've made a little bit of a mistake. I'm going to take this formula and modify it, just so that you can see that you don't need to make a mistake in this. So the another kinematic formula, VF equals VI plus AT. Okay, so the average velocity is going to be VF plus VI over 2. Okay, so the final velocity is going to be 0 because at the bottom of the bending of the knees it's 0, and VI is going to be this velocity here. Okay, so VI from the kinetic energy. Once all that gravitational potential energy is converted to kinetic energy, your initial velocity before the bending of the knees starts is going to be that that VI that we've got down there. So anyway, VI is what we're after. VF is going to be 0. So VI equals negative AT. But remember, we're actually interested in the average velocity over the entire course of the time that the knees are bending. So that's going to be VI plus VF divided by 2. Okay, so VI plus VF divided by 2. VF is 0, so it's just going to be VI divided by 2. So VAV equals VI over 2, and we're going to take that into account a little bit later. Okay, so VI. Anyway, coming back down to our gravitational potential energy equals kinetic energy. VI squared is going to be equal to 2GH, so VI equals square root 2GH. This means that our average velocity, which is what we're actually after, is going to be square root 2GH over 2. Okay, and then we can plug that into our equation up here, which still holds true. We can stick with the VAV. The average velocity is going to be the distance over time, or B over T. So we can find T is going to be equal to B divided by VAV, which is going to be B divided by square root 2GH over 2, which is equal to, okay, there's a few more little tricks still to go, and I'm sorry this video is so long. It's going to end up being 2 on YouTube, but this is going to be 2B over square root GH, 2GH, sorry, and little trick just to get down to the final thing. 2 to the power of 1 is 2. These are all to the power of 0.5 if you get rid of the square root. So 2 to the power of 0.5 means we're going to cancel out that 2 to the power of 1 up the top to find 2 to the power of 0.5 times B divided by square root GH, which if we're to rearrange this, it's going to be B square root 2 over GH, which I think is what we were after in the first place up there, B square root 2 over GH. So there we go. A little bit awkward, a little bit rambling, terribly sorry for that, but you can fast forward. If you got to this point, you probably didn't fast forward, but it would have been useful.